di kota
Di
Pinengka.
kota di Kota Baharu, Kelantan.
Oh, Kelantan. Ya, baik. Di kota Kelantan. Nah, rumah sekarang di Jalan 1, Taman Behor, Goncarjaya, nomor 25, Tangga Perlis, Malaysia. Baik. Untuk pendidikan, ya, Asosiat Profesor Dr. Ramzan bin Mat Ayub, ini kalau di kami ini S1-nya ya, ini Bachelor Science, Fisika, dia dari University SiN Malaysia, yang di Penang ini Bang ya, Malaysia ya, Penang.
Ya, tidak Pak.
Okay. Untuk Master of Science pun sama, ini bidang fisika dan di University SiN Malaysia Penang. Ya. Lalu untuk PhD, ya, program doktor ditempuh di Microelectronic Engineering, University Malaysia Perlis, Malaysia. Ya, pengalaman beliau di dalam menulis maupun dalam kerja, saya kira saya tidak perlu bacakan satu-satu. Nah, kami yakin bahwa kehadiran beliau ya dalam bidang semikonduktor ini bisa membuat kita katakan berdiskusi panjang, dan kita juga bisa katakan membuat satu kolaborasi. Ya, mungkin sedikit kami izin bahwa untuk Unimap ini kami pernah diundang sebagai visiting lecturer di sana 1 tahun ya, terhitung 2005 sampai 2006. Nah, kami dengan Asosiat Profesor Ramzan bin Mat ini, Matayub, biasanya kami panggil abang, jadi biasanya kami kalau katakan apa, WA nanti chatting kami panggil abang, karena memang kita sudah kenal baik ya, gitu ya Bang Ramzan ya. Baik, itu sekilas CV beliau ya. Saya kira kita simak dulu pembicaraan beliau dalam bidang semikonduktor ini. Ya, Bang Dr. Ramzan bin Mat Ayub, kita punya mata 1 jam ke depan ya. Nanti insya Allah di akhir ini kita masih punya masa 30 menit untuk kita diskus gitu. Ya, baik, saya kira demikian. Silakan ya Bang Dr. Ramzan, kami persilakan.
Assalamualaikum dan terima kasih kepada Bang Dr. Irzaman di atas introduction, di atas generosity memberikan satu introduction yang sangat baik lah. Saya cuba share screen dulu ya. Adakah boleh nampak saya punya screen?
Oke, boleh Bang.
Alhamdulillah. Jadi saya mulai dengan salam perkenalan, salam ukhwah untuk bapa-bapa, ibu-ibu, anak-anak pelajar di IPB. Dan juga di Malaysia masih lagi dalam suasana perayaan lah. Masih lagi dalam suasana Syawal. Jadi rasanya tidak terlalu terlambat untuk saya mengucapkan salam Aidilfitri, salam Lebaran untuk saudara-saudara yang berada di sana lah ya. Jadi sebelum saya mulai, saya ingin nyatakan bahawa saya malu untuk mengaku sebagai pakar atau sebagai pakar di dalam bidang ini. Ada sedikit pengalaman kerja, sedikit pengalaman dalam akademik, sedikit saja yang tahu. Banyak yang tak tahu. Dan yang tahu pun banyak lupa juga. Jadi atas semangat perkongsian, atas mak ukhuwah, saya terimalah pelawaan daripada sahabat saya, Prof. Irzaman, untuk kita berdiskusi, bertukar-tukar fikiran lah. Jadi beliau mencadangkan kepada saya untuk memberikan sedikit perkongsian tentang silicon nanowire Field Effect Transistor. Tetapi apabila saya buat nota, saya merasakan lebih baik, lebih memberi manfaat terutama kepada para pelajar lah. Sekiranya saya bagi satu yang lebih luas perspektifnya. Sebab seperti di sini juga, di Malaysia juga ramai pelajar postgraduate sama ada masters ataupun student yang cuba membuat kerja-kerja yang melibatkan very advanced MOS structure. Tapi yang basic-basic tu mereka tak berapa tahu. Jadi saya rasa lebih bermanfaat sekiranya saya dapat berikan satu broad perspektif, walaupun saya terpaksa compromise lah. So bila topik tersebut terlalu broad, maka kita tak dapat pergi kepada kedalaman yang sesuai. So saya cuba compromise lah supaya saya dapat berikan suatu gambaran tentang macam mana apa nama ni advancement dalam bidang microelektronik, nanoelektronik dilakukan, dan apakah faktor-faktor ataupun the driven force yang menyebabkan modifikasi improvement tersebut dilakukan, dan semuanya bertunjang kepada fundamental teori, mathematical foundation yang mana kita terutama para pelajar perlu ketahuinya supaya kita dapat appreciate, kita dapat memahami kenapa sesuatu structure, sesuatu teknologi itu berlangsung ataupun dibangunkan. Saya harap ini berkenanlah pada pandangan ataupun pada penerimaan panitia di sana lah. Harapkan begitulah ya. Adakah tuan-tuan jelas dengan suara saya?
Ya, jelas, Bro.
Ya, jelas, Bang.
Alhamdulillah, terima kasih.
Ya.
Okey, jadi seperti yang saya selalu pesan kepada pelajar saya lah, fizik ni, jangan hafal, don't memorize. You learn and understand. You have to have the overview picture, the right perspective, the right paradigm. Then you understand the plot. So you don't have to memorize. Understand, learn, and understand. Jadi di sini ialah sedikit sebanyaklah apa yang telah nyatakan tadi. Saya akan cover, saya akan tunjukkan the evolution of MOSFET structure from conventional, from the old one, conventional one, to the advanced structure, such as FinFET, silicon nanowire, FET, and so on. And in order to understand this, to appreciate this, is essential, is very crucial to understand what are the driving force. Why people do this? Why people do that? What are the compromise? What are the trade-off? And all this begin from the theoretical, from the basic theory, of material, of device, and so on. So once we understand that, then we can appreciate. The beauty, of the technological advancement. Okay, so that is more or less covered my presentation today. Okay, so saya bahagikan perbincangan ini kepada dua bahagian lah. Yang pertama ialah saya rasa perlu, tapi saya tak akan sentuh semualah. Ada yang part yang saya akan detailkan, ada part yang saya akan tunjuk sekali lalu saja. Supaya kalau let's say student mereka rasa mereka tidak memahami sesuatu konsep ataupun teori, mereka boleh senantiasa refer balik kepada nota yang diberikan inilah. So saya akan tunjukkan ataupun saya akan bagi sedikit overview secara sepintas lalu tentang teori semiconductor material, basic devices seperti MOS capacitor, in order to understand the more advanced or more complicated structure such as MOS transistor and other advanced MOSFET, right? Okay, so from there I'll describe the important aspect of the MOS technology, which is the model, which is the IV model, and this IV model is very crucial in order to predict, to simulate the device, to simulate the circuit, all right? Okay, so I'll go to the more scaling and so on, and then only we discuss a little bit on the important, on the significant advanced metal oxide semiconductor field effect transistor. This include the what we call the gate all around, which silicon nanowire belong to this category. Okay. Okay, so the semiconductor industry is quite complicated. The final goal is to produce, to design, to fabricate, and to produce the high performance integrated circuit. And we have so many layers, so many disciplines involved in producing. Ada apa-apa masalah? Tak ada, okay. Okay, so this the whole industry involves so many disciplines in order to produce a high performance integrated circuit. So we start with material. So we need to have the good understanding on the material itself, the behavior, the behavior of the material, the carriers, the behavior of carriers, and then from the material, in order to produce, in order to construct the basic device, the basic structure, such as PN junction, capacitor, diode, and so on, we need to have the proper technology, a proper way of constructing that devices. Okay, so we need to know what is the oxidation, the ion implantation, the photolithography, on how we pattern, how we transfer the design, the pattern from design onto silicon. Okay, so this belongs to what we call the semiconductor process technology, and because the structure is quite complicated, right? So you need to have the module, we say, such as well technology, because you need to put the both N-type and P-type transistor onto a single, the same substrate. So you need to have the good way of controlling the substrate behavior. So this where the well technology comes into play. And also the isolation technology, because you have billions, millions of transistors put into a small silicon area. And these millions and billions of transistors need to be electrically isolated to prevent from crosstalking and so on. So that's where the isolation technology comes into play. And from here to the until we manage to produce the high performance IC, there's so many things, so many expertise needed that need to be acquired. And this thing, you cannot have the trial and error, because the cost to produce a microchip is very expensive. So you need to have a kind of prediction, simulation, and this comes from the basic. You need to have the model. You need to be able to model the process, the material, the device until the circuit level. Okay, so this where the very large scale integration, computer aided design, comes into play. So when we manage to model, to give the mathematical presentation of the process technology, of the device technology, of the circuit technology, then we can be able to reduce the manufacturing cost and to reduce the time frame from design design to market. Okay, so that is basically the summary of the main activities in semiconductor industry. Okay, so we can summarize that the goal of semiconductor device technology is, one, is to produce the highest performance chip, highest performance integrated circuit, while minimizing the cost. Okay, so that is the goal, the major goal of semiconductor process or semiconductor device technology. And the performance is normally measured in, one is the speed of the transistors, the speed of the integrated circuit, and the speed is basically the measurement on how fast the signal can be transferred from terminal to the other terminal, or the data can be processed. So it depends, and this speed is the function of the transistor's channel current, the channel current, and also the conductivity of the conductor, and also the how do we minimize the parasitic capacitance, the RC delay that coming from the multi-level interconnect, from maybe more than 10 layer of interconnect that will produce the RC delay, that will hamper, will delay, or will slow down the movement of the speed of the signal being transferred. Okay, so this is where the high K material, high conductive metal from aluminum, copper, and so on. So that is where this high conductive metal comes into play. And for the low K material is how do we reduce? The RC delay that will hamper, will slow down the speed of our device. So that is the first one. The second one is the power dissipation. We want to reduce the power dissipation, and this can be done by minimizing the off-state leakage, the off-state leakage current that tunneling or that conducting through the channel while the transistor is turned off. So this is the main driving factor of the technology, to maximize the on-state current and to minimize the off-state leakage current. So normally this need to be trade-off, because most of the advancement will increase the on-state current, but at the same time it will also increase the leakage current. So the structure, the modified structure, so need to compromise this, need to trade off between ion and ion, and this bring to the silicon nanowire, field effect transistor, and other advanced structure. Okay, so this is the been done by the what we call scaling. So we reduce the dimension, the geometry of the devices of most transistor while optimizing this ion over I-off ratio. Okay, so that is the basic or the driving factor behind the advancement of the technology. And the scaling down is can be seen from this. This is the old data. So process mean this is the gate length of the transistor, 10 micron, back in 1971, and this is the chip area, the silicon area. And with this technology, we can only put around 2,000 transistors. But due to the scaling down, when we miniaturize the transistor down to, for example, 22 nanometer channel length, So we can put 5 billion transistor in very small area of silicon. So okay, so that is the role of scaling in the technology advancement in the semiconductor technology. Okay, as I said that the ability to predict the behavior of the device, of the performance of the device is very crucial. So it's normally done using based on 5 fundamental equation that from this fundamental equation, when we solve this 5 equation, we can predict, we can calculate what is the performance of transistor, what is the behavior of the signal that going through the channel of the transistor. Okay. Okay, so the first equation is called Poisson. I think this is very important. It's very important that this equation governs the charge distribution for the electrostatic carriers inside the semiconductor material. And the other question describe the distribution of how electron and hole behave under the electric field. Okay, and the current density also the calculate the behavior of electron and hole, so we can predict, so we can calculate based on this equation, we can calculate the IV, the behavior of current under the influence of the voltage or the field at the gate. I think maybe we discuss more about this later. Maybe some of you maybe not can appreciate what is the gate and so on up to this point, but we'll cover this. I will cover that after this. Okay, so it start with atom. This is the old model of atom, but for the educational purpose, we still can use this. So electron it can be described as the wave as well as the particle, but in this case, we assign electron, we treat electron as wave. So electron has the specific wave function. So for example, say if we have a carbon atom, so if the atom is isolated, so every atom has the unique electronic structure. But when we put the atom all together, the wave function will overlap. So it will redistribute and form the new configuration of the energy level. And we can differentiate these two energy level as the conduction band and the valence band. Okay, and the energy that between the conduction band and the valence band is called the band gap, where this is the forbidden energy level. No electron or no carriers can occupy this level. Okay, so this is the characteristic of material. This is the identity of material. Every material have different energy band diagram. Every material have different band gap energy, and these properties describe the uniqueness of the semiconductor material, as we can, and we will see after this. Okay, so this brings us to the classification of material into the conductor, semiconductor, and insulator. So, for example, in conductor, the conduction band and the valence band is overlapping. So above the apa dipanggil Allahu Akbar, the absolute temperature, the 0 Kelvin temperature, the anion, the electron, the most of the carriers in the metal is available for the conduction, can participate in the electronic or electrical conduction. Whereas for the insulator, the band gap is relatively larger to the other material, so it's very hard for the electron to be excited from the valence band to the conduction band. So making this type of material will resist the flow of electrons. So we can say that this is insulator because it will resist the flow of electron because the scarcity of the carriers inside the material. Semiconductor material, the band gap is in between. It's between conductor and insulator, and it's relatively easier for the conductor material to the semiconductor material to have the right amount, the adequate amount of carriers, mobile carriers in the conduction band. And furthermore, we can engineer this. We can engineer in such a way that we can improve, we can increase the concentration, the carrier concentration in the conduction band of the semiconductor material. Okay, so this is more or less the classification of the material based on the electrical conduction. And in order to predict the behavior of carriers inside the channel of the transistors, we need to be able to calculate, to predict the probability of carriers inside both the conduction band and the valence band. And this can be done using what we call the energy distribution function. So based on this, this is mechanic statistic. Based on this function, we can calculate, we can predict the availability of carriers inside the conduction band as well as the valence band. Assalamualaikum panitia. Adakah masa kita macam mana?
Ya, boleh terus, Bang.
Boleh terus ya. Saya takut macam lambat sangat.
Saya paham.
Okey, saya akan lajukan sedikit lah. So this is the distribution function that normally used to calculate or to predict the availability of electron, because electron belong to the fermion, the elementary particle under the class of fermion. So Fermi direct distribution is used to calculate, to predict the availability of electron in the conduction band. So we have other distribution, but this is not related to what we discussed now. Okay, so we know that at zero temperature, at absolute temperature, all the electron will occupy the valence band. But as we raise the temperature, some of the electron in the valence band will gain enough energy to be excited to the conduction band. For pure semiconductor, this excitation or this carrier generation is called the electron and hole pair generation. So one electron will be excited to the conduction band, leaving one hole will be created in the valence band. So as a result, in this intrinsic material, the number of electron and hole will always be at the same. Okay, so at room temperature, the electron and hole concentration is roughly around this figure. But this electron and hole concentration in intrinsic semiconductor is not enough to participate in to give the meaningful conduction. So it need to be increased. The number of electron and hole need to be increased in order to give us the significant current. So this can be done by doping. So that's why it's called the intrinsic semiconductor. So intrinsic semiconductor means that pure semiconductor. In this intrinsic semiconductor, the number of hole and electron is always the same. So in order to increase the number of hole and electron in the semiconductor need to be doped. So doping is the process of introducing the impurities, and these impurities will increase the number of electron or hole depending on the type of the dopant. So say we dope the semiconductor material with what we call the donor type. The donor type means that the dopant, the impurities will contribute electron to the material. So in this case, we deposit or we dope, we introduce impurities, we introduce arsenic or phosphorus. So the arsenic and phosphorus will occupy the energy level that just below the conduction band. So once we give the enough energy for this electron in this energy level, so one electron will be excited to the conduction band without creating the hole, a hole in the valence band. So as a result, we managed to increase the number of electron in the conduction band without increasing the number of hole in the valence band. So this material now, the majority carriers in this material now is becoming electron. So electron is the major carriers. So that's why this type of material is called the n-type semiconductor. The same thing apply when we introduce the impurities such as boron. So boron will occupy this energy level. So when electron is excited from this valence band to this energy level, so hole is created. Hole is created in the valence band without creating electron in the conduction band. So as a result, this metal become p-type. So the major carriers in this metal is hole. So therefore, in this extrinsic material, by using doping technique, we can create the electron and hole without creating their pair. Okay, so next is we want to estimate. The number of carriers, the number of electron and hole in the respective energy level. Okay, so I just summarize the main result. So the intrinsic hole concentration, sorry, the electron concentration in intrinsic material is given by this expression. So it basically depending on the temperature and depends on the magnitude of the separation between the intrinsic Fermi level and the conduction band. And the same thing goes for the hole concentration. It depends on the temperature, and this basically showing the amount of doping, the amount of impurities being introduced inside the material. So the more impurities being doped, being introduced into material, this energy level will be separated. Will be more separated. Okay, so this is what the equation tells us. And okay, so for the extrinsic material, the number of hole concentration inside the material is given by this expression. So if you look at the energy band diagram, so we have here the valence band, and here is the conduction band, and this is the intrinsic Fermi level. So if we dope the material with anti-impurities such as arsenic or phosphorus, the Fermi level will become closer to the conduction band. So this is N-type material. For P-type material, when we dope, the more impurities we dope into the material, the Fermi level will become closer to the valence band. So this is illustrated by this equation. So if you want to have more more electron and more hole, what you need to do is you need to increase the doping concentration. You need to put more impurities into the semiconductor material. Okay, so this is showing basically the same thing, showing that the new Fermi level, as a result of the doping, as a result of the impurities being doped into the material. So for the p-type, the Fermi level will become closer to valence band. For the n-type material, the Fermi level will become closer to the conduction band. Okay, so the larger, the more impurities you put inside the material, the more this will go will go further from the intrinsic Fermi level. Okay, so before we go into the MOS transistor, the field effect transistor, is very important to understand the basic capacitor, because this is MOS transistor. So we have a 4 terminal. So we have the metal, oxide, semiconductor, and this is the impurities. For example, say this is p-type semiconductor, and the source and drain, we need to put the n-type. So different, the opposite material. But this MOS transistor is constructed based on MOS capacitor. So MOS capacitor is the heart of MOS transistor. So if you want to understand the behavior of MOS transistor, is very important. It's crucial to understand the MOS capacitor. Okay, so the ideal capacitor, the ideal MOS capacitor is with the assumption, if we assume that oxide is free from impurities, oxide is free from impurities. So this is oxide, the perfect oxide. So if the oxide is perfect insulator, and no matter the biasing that we put at the gate with respect to the source or ground, the current, there will be no current. There will be no current flowing through the outside. So we call this as the ideal MOS capacitor. And so how do we calculate? What happened when these two type of material, P-N junction, P-type semiconductor and N-type semiconductor, being brought together to form the metallic junction? Okay, so the Fermi level in both material will be aligned. So that is the important assumption that need to be done in order to understand, to describe the behavior of the MOS capacitor using the energy band diagram. Okay, so once we form the metal junction between metal oxide and semiconductor to form the MOS capacitor, so this is the energy level that being formed, where the Fermi level will align in all these three materials. And this brings us to the four important conditions. It depends on the biasing that we put at the gate. For example, so this is the metal oxide and this is P-type semiconductor. So in P-type semiconductor, the majority carriers is whole, is positive charge, we could say. So once we bias, we put the negative biasing at the gate, the metal will be deposited with the electron. So as a result, hole inside the P-type semiconductor will respond to the position of the electron at the surface. So as a result, the hole inside the P semiconductor will accumulate at the surface. So we call this as the accumulation. Okay, so I think I just go through this. Okay, so what happened? So what happened when we bias the gate, the P-type PMOS capacitor with positive bias? So in this metal, the positive charge will be deposited in the metal. So as a result, the majority carriers hole inside the semiconductor will be repelled, will be depleted. Okay, will be depleted. So we call this as the depletion. So when we increase the biasing at the gate, the the hole will be depleted further from the surface until we reach a condition where this surface become inverted from P-type material to the N-type material. So the majority carriers at this surface is electron. So we call this as the strong inversion condition. So this is condition where the channel is formed at the surface, at the semiconductor surface. Okay, so this is very important to calculate, in order for us to calculate the threshold voltage. At what biasing at the gate, the channel will be formed. The current will start to conduct through the channel, through the transistor channel. Okay, so to summarize this, okay, so the threshold voltage is given. Threshold voltage means that the gate voltage at which the semiconductor metal is inverted, in this case from P-type to N-type. And if we give the enough potential difference between the source and the drain, the channel will be start conducting. The current will start flowing from this to terminal, and this is given by this condition, where QD is the depletion region charge and CI is the insulator, the capacitor of the insulator, and this is the Fermi potential. Okay. So, but in the actual case, the dual function between semiconductor and metal is different, and also the insulator is not perfect. There's a lot of impurities inside the insulator. So, in order to compensate, in order to take into account this non-ideal case, so we can express the threshold voltage of the MOS capacitor by taking into account what we call the flat band voltage. Flat band voltage means that without any biasing at the gate, so the energy level at the surface will be bending. So in order to compensate this, we need to put this into the expression for our threshold voltage. Assalamualaikum. Nampaknya saya ambil masa banyak sangat lah. Saya nak tahu macam mana panitia dengan kita punya timing.
Oh, boleh.
Adakah boleh lagi Bapak Irzaman?
Oke, 20 menit lagi, Bang.
Okey, insya-Allah saya akan lajukan. So saya sudah selesaikan yang part pertama. Jadi my intention if apa nama ni, the student can have the some of the ideas lah, ada idea lah on how this apa nama ni, the basic concept or theory that govern the technology, Okay, so I continue with the kita dah bincang tadi lah. This is the Field Effect Transistor, and this is the basic construction of the MOS transistor. So we have the gate, we have the insulator, and we have the semiconductor body. Say this is P-type, so we need to construct this terminal with the opposite type of material. In this case, is N-type. And since we have millions of transistors put inside a very small area, so we need to have a good isolation. So the transistor need to be electrically isolated between each other, and this is the one of the critical technology in semiconductor manufacturing, to have good isolation of transistor, good electrical isolation between transistors. So what is important here is we have two parameters. Okay, so when we turn on the transistor by biasing at the gate, in this case is positive biasing, because we have the P-type, we need to invert the P-type. So this surface need to be inverted to the N region or N semiconductor. So once we apply, we increase the gate voltage, so we will reach the level, the situation where the threshold voltage is achieved. So we have the current flowing through the channel until certain voltage, where if we keep increasing the gate voltage, the current will be saturated. Okay, the current will be saturated even though we keep increasing the biasing between gate and the source. So this is called the ion, the on-state or the drain current, the on-state current that flowing through this channel. Another case is even though we didn't apply any biasing between gate and the source, there will be a small current flowing through this channel. So this is called the off-state leakage current. So the goal, the philosophy of the improving the performance of the transistors is by through maximizing the on current while at the same time minimizing the leakage current. Okay, so that is the most important thing. So this is the most important thing that driven the improvement or the advancement of the MOSFET structure. So we want to have the ion as large as possible while maintaining smaller or small leakage current. So this can be translated into high power, low speed devices. Okay, and in order to do that, we need to have some ideas. We need to be able to calculate the behavior of current flowing through the channel, and this can be done from the knowledge of the charge. If we know the function, if we know what are the parameters that govern the charge in this inversion, in this region, and the charge in this region is given by the capacitor. So this is the capacitor that form between the gate and the semiconductor, and the biasing between the gate and the source, and the threshold voltage, the gate voltage at which this channel will start to conduct, and the voltage, the potential difference between the source and the bulb. Okay, so if we know this, we can calculate the drain current based on this expression, based on this relationship. We know that the drain current, the current that flowing inside the drain is given by the width of the transistor, the charge in this inversion region, and also the mobility, the speed of the carriers going through the channel. And the speed of the carriers going through the channel is given by the mobility. So the mobility of electron in this case, times the electric field that drive the carriers through the channel. So if we know this, we can estimate, we can calculate what is the drain current, what is the current that flowing or conducting through the drain. And by some calculation, so the drain current can be calculated, can be expressed in this by this relationship. So we have the drain current is dependent on the W, how large, how wide is your transistor. So the wider the transistor, the more drain current that you have. Also the length, the channel length. So this is the channel length. So the shorter the channel length, the higher the drain current. The gate capacitance, the larger the gate capacitance, the more current that you've been able to produce, to to flow through this channel, and also the mobility, the mobility of your of carriers, either hole or electron, and also the dipanggil the biasing, the potential difference between the gate and the source, as well as the drain and the source. And this IDS is drain current through the channel. This expression describe the current in this region. We call this the linear region. Okay, so but we also interest to know what is the drain current during the saturation, at the saturation region, where the transistors is producing the maximum current. Okay, so it can be calculated using some expression. So we can express the saturation current. ID set is the saturation current, the maximum current that going through the channel. So it is given by this expression. Okay, so now we have the expression for both linear region as well as the saturation region. Okay, so this is to give the idea of basically there are so many things, there are so many variables that need to be refined, to be considered in order to give an accurate presentation of the behavior of current flowing through the channel. So one of the important consideration is called velocity saturation. But I believe we don't have time for this. So we skip this to give the idea that there is the condition where velocity saturation, the carrier's velocity will impede the behavior of the transistors, and this is called the short channel transistors. So we need to calculate, we need to consider this while we do the estimation, while we do the prediction on the behavior of current flowing through the transistor. Either this particular transistor is experiencing the short channel behavior or not. Okay, so there are expressions to deal with this limitation. Okay, so this is just to illustrate the issue, the limitation that we're dealing with. So to just to give the idea, so the more accurate the model, the more factors that need to be considered. The more computing time, the effort is much. You need to put more effort in order to calculate the behavior of the dipanggil IV through the channel with acceptable accuracy. Okay. I believe we do have time for this. But this just to illustrate. The CMOS inverter is the basic building block of the ICs, and the speed of the ICs is very much dependent on how fast the signal is transferred through the CMOS inverter. Okay, and the speed is depending on the drain current. So the larger the drain current, the faster the speed the signal can be transferred through the terminal. So this is one of the main reasons why the improvement or the the development of the transistor is geared towards increasing, maximizing the drain current, because the larger the drain current, the lower the propagation delay, which translated into the higher speed, the faster the signal or the data can be processed. Okay, so this is all this improvement is achieved through the scaling, but I believe we don't have time for this. So scaling is basically following what we call the Moore's law, and there is a body that that gives some prediction on how the technology should be driven. So the body is called the ITRS, International Technology Roadmap for Semiconductor, and this roadmap gives the manufacturer the wafer fab of some ideas. So where is the direction? That we should be going based on, for example, based on what is the maximum current, the ion that we should be targeting. What is the I-off? What is the leakage current that we should be minimizing in order to target to certain application? So that is the role of the international technology roadmap for semiconductor. So from there, we have the improvement. For example, from 90 nanometer to 65 nanometer technology node. So based on the study by this committee, they showed that strained silicon should be able to meet this criteria, to meet this device performance. We know that silicon, if we compare silicon with other materials such as germanium or other compound semiconductor, the mobility, electron mobility or hole mobility in silicon is relatively poorer. But to migrate from silicon-based process to the other material is very hard, because the industry is, for the whole world, is basically tied up to silicon. So for the immediate improvement, there is a way to improve the mobility, to increase the electron and hole mobility. So this comes under what we call the strained silicon. So by using strained silicon, we manage to increase the mobility of the carriers. As a result, this will increase the drain current, which in turn will increase the performance or the speed of the transistors. But to a certain level, the strained silicon will be no longer capable of producing the device with the targeted performance. Okay, so it's anticipated that high-k material, metal gate will be able to give the circuit designer, chip manufacturer, the intended performance for the targeted IC, for the targeted products. Okay, so this goes until the new structure, the revolutionized structure is needed to bring the industry, the semiconductor industry into the intended performance. Okay, saya akan banyak cut corners lah ya. Okay, so this is the role of the ITRSS to give some guideline to the manufacturer, to the device engineer, to the circuit designer on what kind of process technology that they should be eyeing for, they should be targeting for. Okay. Okay, so this is the summary of the previous slide. Okay, so basically the scaling will give some constraint, will give some pressure to both device and process. For example, so this is the original structure, MOS structure, that say we are going to shrink, we're going to scale down to certain dimension. Okay, so as a result, the structure will become smaller. So we have issues, we have a limitation with lithography on how do we transfer the pattern, the smaller pattern from design, from the mass to the silicon. And also we need to produce high quality ultra-thin oxide. So this is become major issues because of the tunneling and so on. And also the dopant distribution, because the spacing between structure is now cramped together. So dopant distribution is very important issue. So this translated in thermal budget and so on. Okay, so many issues related to scaling that need to be solved. Okay, so I just highlight three main important. So when we scale down the transistors, there are so many device issues. So I just list down, I just briefly discuss the three main issues. One is the sub-threshold current, means that while the device is turned off, it not really turned off. There's some current still flowing, even though the device is intended to be turned off. So that is called the sub-threshold current. Okay, so say we have for NMOS, so that say the threshold is 0.2 volt, there shouldn't be any current here because the device is supposed to be turned off. But in reality, because of this situation, there'll be some current flowing through the channel, even though the transistor is not supposed to be turned on. Okay, and then this sub-threshold current is normally described or subscribed. I think that's not the good words lah. It's normally presented, okay, as sub-threshold swing S. So this sub-threshold swing is the manifestation, is the representation of the sub-threshold current that need to be reduced, need to be minimized. So how do we do that? So this is the conflicting scenario that we need to do. We need to compromise. So in order to reduce the swing, the threshold swing, we need to produce a larger gate oxide capacitance. But increasing the gate oxide will increase or will introduce other issues, other problems, but such as reliability, current tunneling, due to direct tunneling, due to fallen up hand tunneling, and so on. So this is need to be compromised, and we need to reduce the depletion region capacitance, but this will impact the substrate doping, so will impact the punch through and so on. Okay, so this is among the device requirement, but as a result of meeting this requirement, we will introduce other issue. So this is the trade-off that need to be done in order to reduce or to solve one issue, but at the same time, we need to take care of the other issues that surface. And another major issue is VT roll-off. So from the expression, from the threshold voltage expression, the threshold voltage is not supposed to be dependent on the gate length, but as we approach the short channel effect device, the VT becomes dependent, on the gate length, and this need to be taken care of. Okay, so this is the other issue, and we have the as the previous case, there are conflicting requirements that need to be trade off, such as the junction depth. The roll-off, the VT roll-off need for the lower junction depth, lower depletion region width, lower gate oxide thickness. But this lowering these three parameters will introduce other issues, other problems that need to be. So this is for the intended structure. So this parameter need to be compromised, need to be carried off. Another issue is the tunneling, the tunneling through the energy barrier. If the gate oxide is thin enough, so some electrons, some carriers will be tunneling through the barrier by Follow-Nordheim tunneling. And if we keep reducing, thinning the gate oxide thickness, some carriers will be able to penetrate, to tunnel through the barrier using the mechanism known as the direct tunneling. Okay, so we come to the last section. So I'll go very briefly. Saya mohon maaf, berbanyak kemaafan. Panjang sangat. Okay, so this is more or less the improvement or the structure, the advanced structure that been studied, that been proposed by the ITRS. So there are so many ways, so many possibilities, such as FinFET, silicon nanowire, silicon nanotube, and other substrate, such as compound semiconductor and so on. So one of the candidate, it's not candidate this whole thing, but one of the immediate migration from the conventional CMOS, conventional MOS, to the more advanced one is using shallow junction and metal source ended, and this come with benefit and problem as always. You improve some, you gain some, you lose some. So this is the problem with shallow junction as well as the transistor with the metal source and drain. And further improvement is using the ultra body MOSFET, because now we control the channel at the gate. So we can control the channel at the surface. But below this, the gate can no longer have control. So if we can reduce the thickness of the silicon of the substrate, so the gate will have more control on both ion and ion. So that is the idea of the philosophy behind reducing, thinning down the substrate. So this we call ultra thin body, and the same thing goes for the SOI. The silicon thickness is very thin, so as a result, gate can have more control to the conduction of electron or hole in the channel. Either is the on-state current or the off-state current. So FinFET was introduced to have a better control. So we have, you can control the channel by using 2 gates, using multi-gate. So you have control over here, you can control over here. So you have the better control. You can have the better compromise, better trade-off between the I-on and I-off. Okay, so some of the FinFET structure can be employed using silicon nanowire. So using silicon nanowire, we can control the channel from all the direction. Channel is surrounded by the gate. So as a result, the on-state current, the off-state current, the current that flowing through the channel can be better controlled by the gate. So the I-on and I-off ratio will become better, will become easier to be optimized. Okay, so that is the philosophy behind the channel that being surrounded by the gate material. So this is the same thing. So we have many type of so this can be approached in many ways. So one way is the FinFET. So as you can see that even using FinFET, the channel is not we cannot fully control. We cannot fully control the channel because the gate only controlling this part, but this part is beyond control. But by using the apa dipanggil the structure that totally surrounded by the gate, we can have a better control of the current flowing to the channel, and this can be better implemented if you use silicon nanowire. So the ITRS shows that the major improvement can be achieved by using silicon nanowire as the channel for the most transistor if compared to other improvement such as SOI, multi-gate, metal gate, and so on. Okay, so the improvement from the I-on and I-off perspective is tremendous. It's very significant, and this can be translated, or this is shown by this diagram. Okay, so using silicon nanowire, we can improve I-on at the same time maintaining the low level of I-off if we compare to the other direction, other technological improvement. So silicon nanowire is the best approach so far, the best the best approach so far for the advanced MOSFET. Okay, so with that, saya mengucapkan berbanyak terima kasih di atas peluang, di atas perhatian, dan saya mohon kemaafan terlebih masa. Itu saja daripada saya. Terima kasih.
Baik. Ya, terima kasih banyak Dr. Ramzan presentasinya. Prof. Tony, mungkin kami ngelapor, Prof, ini kami di gedung TL jaringan jelek, ini udah 4 kali kami terbental. Kalau dikhawatirkan nanti hilang lagi, tolong diambil alih ya, Prof. tadi ya. Oke, baik, Bapak Ibu, kita punya waktu ya mungkin 10 menit, mungkin 2 pertanyaan saja dari forum, silakan kalau ada ada yang mau bertanya atau menanggapi gitu. Ya, syukur-syukur dari pembicaraan ini kita bisa merajut silaturahim dan kolaborasi. Silakan Bapak Ibu, boleh langsung raise hand, tunjuk tangan, ya, mungkin gitu ya. Baik, ya silakan.
Mau menyapa dulu? Oh, sudah ada yang bertanya? Mau menyapa dulu, Prof. Ramzan. Gimana kabarnya?
Ya.
Abang, baik?
Alhamdulillah, syukur
Oh
seadanya.
ya, Alhamdulillah.
Prof Tony.
Ya, apa kabar? Sehat-sehat ya, baik ya.
Baik, Alhamdulillah. Tapi saya
Ya.
mohon maaf lah, terlebih masa.
Ya, ya, tak apa. Ini banyak apa ya, pengalaman terkait macam-macam device ini ya. Nah, alhamdulillah kita juga ada bergerak di bidang fabrication sensor, detektor, and device untuk material semiconductor ya. Ini mudah-mudahan ini Pak Herianto, Pak Erus yang terkait dengan fabrikasi sensor maupun MOSFET mungkin ya Pak Heri ya, dengan metode macam bisa bertanya nih, sehingga mungkin bisa nanti lebih dalam lagi, mungkin bisa ada yang bisa dikolaborasikan dan sebagainya. Nah ini saya berharap nih dua ini bertanya. Ya, ya salam Prof. Ramzan ya, mudah-mudahan lancar ini semua.
Insyaallah.
Ditunggu ya, mau ke Bogor ya, Insya Allah ya.
Rancangnya lah ada, Prof udah bagi maklum lah. Ada perancangan untuk
ya,
ke Bogor.
Alhamdulillah sudah ada perancangan ya, Insya Allah terlaksana.
Insya Allah.
Ya, amin.
Sebab Prof udah jangka kan, kalau boleh lah IPB akan hancurkan bond untuk edisi akan datang.
Ya, Insya Allah kami siapkan. Mana Pak Heri, Pak Erus?
Silakan Pak Dr. Heri.
Mungkin tak apa Prof, lain kali pun boleh, kita boleh sembang. Semua saya nak tanya lah, di Indonesia ada wafer fabrication facility tak?
Mungkin
ada
waktu sekolah itu mereka lulusan Jepang ya. Jadi nice ya. Nah ini Pak Heri udah siap nih. Ya, silakan Pak Heri.
Ya, baik. Terima kasih Pak Nani. Terima kasih Pak Ramzan. Assalamualaikum Prof. Ramzan.
Waalaikumsalam warahmatullah.
Ya, senang sekali tadi melihat presentasi dari Prof. Ramzan. Sepertinya sudah banyak sekali pengalaman di device, terutama transistor ya Prof ya. Ya saya tidak asing dengan istilah-istilah tadi ya, karena saya memang S3-nya kemarin risetnya tentang transistor juga. Tapi menggunakan polimer, Prof. Polimer yang dipabrikasinya dengan thin filmnya menggunakan metodenya adalah metode metode basah ya. Artinya menggunakan floating film. Jadi filmnya diterapungkan di atas cairan. Nah, kita gunakan cairan itu gliserin sama dengan gitu. Intinya polimer ini kan dia khas, Prof. Jadi punya kita bisa adjust konduktivitasnya itu berdasarkan bagaimana kita mengarahkan rantai-rantai polimernya. Gitu. Nah, jadi kompetensi saya di sana waktu itu mencoba mendapatkan polimer yang dengan filmnya itu nanti dia satu arah gitu, sehingga meningkatkan mobility-nya gitu. Seperti itu. Nah, kalau misalkan mengembangkan di sini agak terkendala dengan karakterisasi RF-nya. Saya harap nantinya misalkan ada rezeki nantinya bisa di labnya Prof. Ramzan gitu dengan Pak Isam nantinya dengan kita di sini. Kalau di sana menggunakan Prof, banyak yang fabrikasi dan transistor, metodenya basah juga atau bagaimana, Prof?
saya tak berapa kurang jelas pertanyaan Prof Haryanto.
Ya, tadi
banyak
kalau di
banyak
di
banyak
labnya
gangguan
Prof.
suara.
Ramzan ini, oh itu, iya ini agak kurang bagus koneksinya.
Ya.
Jadi kalau di labnya Prof. Ramzan ini mengembangkan transistornya itu menggunakan apa namanya metode fisik atau lebih kepada yang basah.
Oh, okey.
Jadi,
Di sini kita ada dipanggil standard CMOS process. Maksudnya semua silicon base, semua solid state. Jadi apa nama ni, transistor dibina ataupun difabricate lah menggunakan apa yang dipanggil standard process lah, standard CMOS. Jadi saya dengar doktor tadi beritahu ada macam cecair
ya, floating film.
floating film. Kita tak ada capability itulah. So apa yang saya boleh jelaskan di sini, kita hanya boleh fabricate transistor yang berasaskan kepada dipanggil standard semiconductor process technology lah. Kita based on silicon, and then kita ada boleh deposit insulator seperti silicon nitride, silicon dioxide, kita boleh deposit metal seperti aluminium, dan kita boleh, yang penting kita boleh buat patterning lah, kita boleh pattern transfer, kita boleh design masking ataupun topeng, kita design mask, kemudian kita boleh translate, kita boleh transfer the pattern from mask onto silicon, ke atas silicon menggunakan proses fotolitografi lah, di mana kita deposit dengan satu filem yang sensitif pada cahaya. So depending on positif ataupun negatif photoresist lah. So kita boleh patternkan, kita boleh transfer pattern pada design mask tadi kepada silicon selepas kita buat etching semua sekali lah. So itu basic transistor yang kita buat lah. Di sini banyak pengkaji yang sebab transistor yang sebenarnya is quite complicated. At least kita kena ada 4-5 masking step lah, design layer lah. You kena ada source and drain, you kena ada metal punya layer, punya design, you kena ada gate semua sekali kan. It's quite complicated dan kita ada limitation dengan kita punya fotolitografi lah. Untuk buat satu layer, okay. Tapi kalau kita nak align layer by layer, ada masalah. So sebab tu di sini majority kita guna IDE, interdigitated electrode sebagai kita punya transducer untuk apa nama biosensor lah. Sebab banyak yang buat biosensor di sini. Tapi mereka instead of guna transistor, kita guna IDE. IDE very simple, satu layer saja, satu design layer saja. Dan dia hanya involve single metal deposition dan kita patternkan dapat dia punya interdigitated electrode macam ni lah kan. Walaupun dia tidaklah sesensitif seperti MOS transistor ataupun silicon nanowire transistor, tapi kita compromise dari segi senang untuk fabricate. Begitulah lebih kurang ceritanya daripada apa yang dapat saya faham.
Berarti fabrikasinya menggunakan teknologi canggih nih Prof. Harus clean room rupanya nih Prof ya, sepertinya ya. Saya membayangkan clean room ya, karena transistor itu tidak bisa kalau ada impurities sedikit saja.
Betul.
Hilang.
Kita ada clean room dan kita punya mask liner, boleh dia punya resolution, boleh kita boleh produce structure around 1 micron. 1 micron structure kita boleh produce using kita punya existing mask liner lah. Tapi ada lecturer, ada researcher yang dia boleh produce, even though kita punya mask liner dia punya maximum resolution 1 micron, kita boleh produce less than that, 0.5 micron. So dia ada banyak teknik lah, dipanggil size reduction technique and so on. So kalau kita nak produce transistor with smaller geometry, kita boleh. Sebab kita hanya satu dua transistor saja, so tak ada isu.
Baik, Bapak Ibu, ya, ini nampaknya waktu yang ya istilahnya sudah mendekati habis lah demikian. Jadi kami mohon maaf untuk diskusi mungkin tidak bisa ditambah lagi. Ya, terima kasih banyak Pak Dr. Ramzan. Tapi Bapak Ibu, saya padamkan kamera, takutnya spontan kami keluar terpental dari YouTube ini. Ya, baik. Kembali jadi.
Assalamualaikum. Sebelum berpisah, saya nak ucapkan lagi sekali terima kasih di atas kesudian pihak IPB untuk menjemput saya. Dan saya juga mohon maaf lah di atas kekurangan, ketidaksempurnaan dalam penyampaian, melebihi masa dan sebagainya. So kita boleh kalau yalah saudara serumpun kan. So kita boleh bincang, kita ada di sini ada fasiliti yang baik lah. Fasiliti yang baik, agak baik untuk produce transistor, IDE ataupun untuk kerja-kerja yang kita kata signifikan di dalam semiconductor teknologi ya. So kita boleh sharekan fasiliti, kita boleh usahakan untuk berkolaborasi secara lebih dekat lagi lah. Jadi sekali lagi mohon maaf di atas segala kekurangan. Maklumlah orang tua dah nak pencen, banyak lupa dah. Banyak lupa dah.
Prof. Ramzan, masih ada kegiatan nih beberapa menit lagi ini. Kita punya ketua divisi fisika terapan ya, research group in applied physics. Ya, mau present something, apresiasi buat abang ya.
Cantik.
Ya.
Ya, silakan Pak Dr. Mata. Masih di mute Pak Dr. Mata.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
warahmatullahi.
Prof. Ramzan, alhamdulillah pada kesempatan sore hari ini kita bisa mengikuti sharing pengetahuan ilmu dari Prof. Ramzan. Kami ucapkan terima kasih. Jazakumullah khairan katsira. Semoga menjadi ilmu yang berkah. Nah, mungkin dalam kesempatan yang berbahagia ini kami ingin menyampaikan apresiasi berupa Certificate of Appreciation to Dr. Ramzan bin Ayub atas kontribusi kesempatan berbagi ilmu pada IPB Physics Talks yang ke-47 nih, Pak Ramzan. Thank you, terima kasih atas sharing ilmunya. Mudah-mudahan ilmunya berkah. Kemudian juga tadi kita berharap bisa berkolaborasi ya Prof, terkait dengan penggunaan fasilitas pembuatan fabrication semiconductor transistor. Mudah-mudahan ini bisa mendorong kami di Departemen Fisika untuk juga mungkin nanti bisa memanfaatkan fasilitas yang ada. Mungkin di IPB sendiri mungkin sangat terbatas fasilitas, terutama untuk fabrikasi sintesis transistor. Demikian. Terima kasih. Jazakumullah khairan. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam dan terima kasih kembali.
Baik, di penghujung ini kita akan tutup. Silakan Prof. Tony selaku Ketua Departemen Fisika IPB untuk menutup acara Physics Talks yang ke-47. Ya, Kami mohon maaf jika dalam mimpin moderator ini kurang berkenan di hati Bapak. Ya, Assalamualaikum warahmatullahi wabarakatuh. Silakan.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih sekali lagi Prof. Ramzan nih. Alhamdulillah ini bisa sharing ilmu pengetahuan yang sangat berguna. Ya, kita punya minat yang sama di departemen juga terkait riset-riset itu. Ya, harapannya ya bisa, apalagi sebagai implementasi apa itu, kita punya kerjasama ya, kemarin tahun lalu kita tanda tangan apa itu MOU dan sebagainya, tinggal aplikasinya ini ya. Nah mungkin nanti kalau ada kita punya graduate student ya bisa pembimbingan bersama gitu ya dan sebagainya. Kemudian juga dari Perlis kalau misalkan kita juga punya modeling ya, ini Pak Fauzan, kita punya Pak Fauzan itu di FT ya, di INE itu kan juga ada yang modeling ya Pak Mahidin dan sebagainya, combine ya, komplement ya, ada simulasi dan ada fabrikasi. Nah itu mungkin insya Allah kita juga bisa sokong ya untuk kemajuan bersama nih. Alhamdulillah ini mudah-mudahan ke depan nanti ada yang lain-lain kita bisa undang juga ya, Pak Mahidin, Prof. Uda juga kalau ada kesempatan ya. Online itu murah ya, online semacam ini kita juga bisa lebih sering ya. Nah nanti
Ya,
mungkin
insyaallah.
Prof. Irzaman ya yang lebih punya kedekatan emosional ya, kita bisa jalin rajut lebih erat lagi ya. Terima kasih kembali Prof. Ramzan ya.
Ya, sama-sama. Saya juga terima kasih. Jumpa lagi.
Ya, jumpa lagi insya Allah. Ya, demikian Pak Irzaman. Ya.
Ya, baik. Terima kasih banyak Prof. Tony selaku Ketua Departemen Fisika IPB. Ya, kami pun mengucapkan terima kasih banyak kepada Dr. Ramzan bin Mat Ayub, ya, Pak Dr. Mansah, rekan-rekan dosen semua. Saya lihat tadi ada Prof. Husin, Kepala Divisi Fisika Teori, terus ada juga Pak Profesor Akhiruddin, ya, selaku Kepala Divisi Biofisika. Ya, ini ada juga Pak Dr. Setianto dan rekan-rekan sini tidak saya absen satu-satu ya, ada Pak Dr. ya. Makasih banyak dari awal ya Pak ya. Mudah-mudahan silaturahmi ini terus rajut dan tadi diutarakan oleh Prof. Tony ya, dan banyak hal yang bisa kita rajut dan kita bisa kolaborasikan. Ya, saya kira demikian ya, kita akhiri ya acara PC Talks ke-47 ini dengan baca hamdalah. Alhamdulillahirabbil alamin. Ya, baik, saya tutup. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Terima kasih banyak Pak Dr. Ramzan.
Ya, sama.
Dr. Ramzan.
Rekan-rekan semua. Ya, mudah-mudahan berkah ya.
Insyaallah.
Oke. Baik, saya izin live nih. Masih banyak ya. Oh, ini ada rekan-rekan mahasiswa juga semua ya. Baik, yuk. Assalamualaikum warahmatullahi wabarakatuh. Ya.
Waalaikumsalam.